Okay, so for E, it says water has the density of 1 gram per milliliter. Sketch the line representing water on the graph. So if we do a for every statement, for every 1 milliliter, we have 1 gram. For every 2 milliliters, we have 2 grams. 3, we have 3. Water's the only one that's like this. So on my graph, for every 10, we have 10, 20, 20, 30, 30. So this is my water line. The next question asks whether or not they should sink or float. Well, we look at our graph. Substance A is a steeper slope than water, so this should sink because it has a higher density. And this has a less steep slope than water, so this should float because it's less dense than water. So it says to defend your answer, a line with a steeper slope gives you a higher density. Okay, this one was one of the hardest questions. It actually gave you a bunch of slopes or densities and wanted you to graph them. But in order to graph them, you have to be really good at writing for every statements. So for titanium, which is here, 4.54 grams per milliliter. Well, what does that mean? It means for every 1 milliliter, because we're always talking per means 1, for every 1 liter, we have 4.54 grams. Now, if I look at my graph, 1 milliliter is here, but how much is each increment? Well, this is like 10, and seeing 4.54 is really tough. So I could make a line, a dot right here, but there's a better way to do this. Let's look at our scale. Our scale is a whole lot larger than what that is. So we could do possibly for every 5 or for every 10. So for every 1, we have 4.54. For every 10 milliliters, we have, well, this is going to be 10 times as greater. We have 45.4 grams. And this we could graph. We take our 10, which is here, and we take our 45, 10, 20, 30, 45 right here. And that would be a nice point. So I want you to take a ruler and connect this with that right there. Now for copper, our density is 8.96 grams for every 1 milliliter. So again, we write for copper, for every 1 milliliter, we have 8.90 grams. And if we were to do for every 10, this would be 10 times greater. It would be 89.0 grams. Okay, so let's see, do we see 89.0? Well, this is 90, so it would be right here. Make a line. Actually, I'm just going to try to, I want you to actually use a ruler, but I'll do the best I can right now. So this is titanium, and this is copper, okay? And then what we have here for mercury, wanted us to do mercury, for every 1 milliliter of mercury, we have 13.55 grams. Now, if I did for every 10, that would be 135, which is way past our graph. So we can't really do that. We could graph for every 1. 13 is sort of, you can sort of see it, but I would say that's still kind of hard. So instead of for every 10, we could do for every 5. So for every 5 milliliters, we have, well, if this was 1 milliliter, what do we do this number to get for every 5? We would multiply this by 5. So here's my calculator, 13.55 times 5 equals 67.75. So at my 5 milliliter mark, it is 50, 60, 67, which would be about right here. So this would be my mercury. That would be my mercury line right there. And that's all there is to graphing using densities and for every statements. Okay, next, this tells you that you have a cube, and it tells you that each side of the cube is 2 centimeters. And it wants to know, first of all, what the volume is. The volume is length times width times height. 2 times 2 times 2 is 8. And remember, milliliters and centimeters cubed are both equal. Then it wants you to find the mass of these metal cubes. Okay, so in order to find the mass of these metal cubes, which are all 8 milliliters, we need to use our for every statements. So for the lead cube, we go up here and we see that for lead, for every 1 milliliter, I have 11.35 grams. So for every 1 milliliter, I have 11.35 grams. And again, that's for the lead one. So for every 8 milliliters, which would be this Q right here, we'd have, well, how would we get this number for every 8? Well, this is 8 times bigger, so this needs to be 8 times bigger. So 11.35 times 8 equals 90.8. So the mass of this Q would be 90.8. I'll let you get the rest of these. You can do the rest of these by yourself. Look up nickel and then make it 8 times bigger. Look up zinc, make it 8 times bigger. And your answers are the ones that are 8 times bigger. So I'll let you fill that in yourself. Down for number 7, we're trying to figure out whether this girl should throw a ring back at her boyfriend. She did the experiment we did where she put some water in, then dropped the ring in, and then it got to a higher volume. And to get the volume of the ring itself, how do I draw a ring down here? I don't know. Maybe that looks like a ring, probably not. To get the volume, we need the difference. So if we subtract my initial and my final volumes, we get 1.5. To get our density, density is mass divided by volume. They give us our mass up here, 15.28 grams, and my volume is 1.5 milliliters. So when I divide that, 15.28 divided by 1.5 equals, that's a long number. So let's figure out where we should round. You look at your original measurements to figure that out. We have 3 sig figs for my cylinder and 4 for my mass. It's always better as a scientist to be more modest about your answers. If you had a bridge and you were trying to tell people that on a good day it could hold 6,000 pounds, on a bad day it could hold 4,000, the one that's more useful to everybody is the bad day. On a bad day it can only hold 4,000, so you better not go over this bridge without 4,000, more than 4,000 pounds. So this is 3 sig figs, this is 4. We want to round this long crazy number to match our worst measurement, which was 3. So because this is an 8, we'll round this up to 0.2. So the answer is 10.2 grams per 1 milliliter. That's the answer. Well, should she throw it at him? Well, let's look at our densities. The density of gold is 19.13. It looks like that ring was probably made out of silver. And it's not exactly the same, but remember, we all have air in our lab with our slanted desks, or maybe water that was already in the cylinder. So she probably just had some experimental error, and it's probably made of really silver. You can decide for yourself if you think she should throw it. The last one is very similar. It gives you a solid object. And it says that if the density is this, what's the mass? It wants you to solve for the mass of the object. So to figure out the volume, it's the same as the previous problem. We are going to subtract the final volume from the initial, and it gets 10.1. So we know the volume, we want to find the mass. So here's our for every statements. If for every 1 milliliter we have 2.99, then for every, well, we want to find the mass of this 10.1 milliliter object. So you try to do this one. If for every 10.1 we have, well, this is 10.1 times bigger, so this needs to be 10.1 times bigger. So we take 2.99 times 10.1, and we get, all right, and let's talk about our significant figures. Here you go back to your original problem. 3 sig figs, 3 sig figs, 3 sig figs. This should be rounded to what? It should be rounded to 3 sig figs to match the other measurements. Instead of 30.199, it's going to be 30.2. I hope that this makes these problems make more sense. You're going to have similar problems on your quiz on Friday, so make sure you study this worksheet.